Example 1 says, what are the dimensions of an aluminum can that holds 40 cubic inches of juice? Kind of weird to use cubic inches, right? Better to use metric units, cubic centimeters, some number of liters or something. And that uses the least material. Uses the least material. I guess the volume is fixed, 40 cubic inches. And we're trying to minimize the material. That would be proportional to the surface area, or it would be equal to the surface area. Although there'd be a little bit of thickness to it, the actual aluminum. Assume the can is cylindrical, like all cans, or most cans, and capped on both ends. So we're also thinking about aluminum on the top and the bottom of the can. We could also do a similar problem where we take off the top of the can. I like thinking about these problems in a certain kind of way that you will not find in the book. I like identifying what I call the constraint and the objective. The constraint here well, it is constraining us. It's the fact that the volume is fixed at 40 cubic inches. Volume, V, is fixed at 40 cubic inches. That is constraining what's going on. We're not thinking about an arbitrary cylinder. Here's an arbitrary cylinder. We're not thinking about an arbitrary cylinder. We're thinking about one that has a volume of 40 cubic inches. Well, what is the volume of a cylinder? The top of a cylinder is a circle. I'm drawing this three-dimensionally with perspective of some radius r, and the cylinder has some height h. The volume is going to be the area of the circle on the top, pi r squared, times the height, h. That'll be the volume of a cylinder. Pi r squared times h. R and h are variables, you might say, but they cannot vary independently of each other. If, for example, r increases, to keep the volume to be 40 cubic inches, cut that out. To keep the volume to be 40 cubic inches, h would have to decrease. If r increases, h would have to decrease to make this still equal 40. So they can vary, but they can't vary independently of each other. They're related to each other. What is the objective? The objective is the quantity you want to optimize, maximize, or minimize. When I say optimize, I mean maximize or minimize. In this case, we're trying to minimize something. We're trying to minimize the surface area. The objective is to, well, let's put the word minimize in there. Minimize the surface area. But what is the surface area of such a cylindrical can? Well, it consists of the top and the bottom of the cylinder, assuming there's aluminum on the top and the bottom of the can. Each of those areas is pi r squared, and I've got two of them. 2 pi r squared. But then I also have the area around the sides of the cylinder. What's the surface area of that part? I hope it's pretty clear that it should be the circumference of the circle times the height. Does that make sense? Because if you cut the cylinder along a line over here and unrolled it, it would look like a rectangle, and its area would be base times height. Well, the height is h. What's the base? It would be the circumference of the circle. Circumference of a circle, hope you remember, is pi times the diameter, same as 2 pi times the radius. That's the circumference. Then we multiply that by the height to get the surface area around the cylinder. So this is for the top and the bottom, top and bottom. This is for the, what should I call it? The side of the cylinder. Side, circular kind of side, round side. I'll put quotes. This is the quantity we want to minimize, make as small as possible, subject to this constraint. We want to minimize S subject to this constraint. Now you look at the formula for S, you say, I've got an R and an H there. That's a function of two variables. Do I need multivariable calculus? Well, if we weren't thinking about a constraint, we might. But because we're thinking about a constraint, we can use single variable calculus. We can use the constraint equation, the fact, well, that this is true, to solve, for example, for H in terms of R and substitute that in right there and get something that only depends on R. That's probably the simplest way to do it, because if I solve for R as a function of H, I'd have to take a square root. So it's probably simpler to solve for H as a function of R. Look at that equation, pi r squared H equals 40. Solve for H, divide both sides by pi r squared. H is going to equal 40 divided by pi r squared. Substitute that in place of the H here. What happens when you do so? The surface area becomes a function of just R alone. That's what happens. It's 2 pi r squared plus 2 pi r times H, but H is 40 over pi r squared. The pi's cancel, that's nice. One of the r's cancels, right? So this simplifies to 2 pi r squared. 2 times 40 is 80. So we get 80 over r, it looks like. This can also be written as 2 pi r squared plus 80 times r to the negative 1 power. This formula is valid as long as I have a cylinder, which means r can't be negative. Also, r can't be 0 either. I wouldn't have a cylinder if r were 0. It would be a line. If r is 0, it would be just a line, not an actual cylinder with an actual volume. R's got to be positive. There we go. I jinxed it. Oh, working? Okay. R's got to be positive. That's the domain. Domain for the application. It's not that I can't use this equation when R is negative. It's just not relevant for the application when R is negative. Unfortunately, in terms of finding a global minimum here, it seems like the fact that R could be any positive number could be a problem, right? Because think about what we did on Wednesday. We were finding global maxima and minima over closed and bounded intervals. The interval here is really 0 to infinity here, not a closed and bounded interval. So maybe this function's got no global minimum. But we're fortunate it does. How do you find it? Find the critical points, look for local extrema, and then ask yourself, well, are these local extrema actually global extrema? Or in our case, is the local minimum a global minimum? How can that be confirmed? A couple different ways. I'll talk about it when we get to it. So how do we do that? We need to take the derivative. I could label the derivative ds dr or f prime of r, it doesn't matter. Take the derivative here. I'm going to get 4 pi r, and I could use the quotient rule, yes, but because I'm writing it like that, I don't have to use the quotient rule. Minus 80 r to the negative 2. Might be nice to go back and write that as a quotient now. This derivative is undefined when r is 0. So does that mean r equals 0 is a critical point? Well, not really, because r equals 0 is not even in the domain. We're looking for positive critical points. Set it equal to 0. Try to solve for r. Looks complicated. It's easier than it looks. I would add 80 over r squared to both sides and get 4 pi r squared equals, or 4 pi r equals 80 over r squared. Then effectively I'd cross multiply both sides by r squared and divide both sides by 4 pi to get r cubed by itself on the left equals 80 over 4 pi on the right, which simplifies to 20 over pi. And so I guess that means your critical point, your positive critical point, is at r equals cube root of 20 over pi. Use technology to approximate that. 20 over pi is about 6.366. Take the cube root of that, raise it to the 1/3 power. This is about 1.853. Since the units of volume were cubic centimeters, this would be in centimeters. Or they were inches, sorry. Inches. But is it really giving us a minimum surface area? How do we know? We could try using the first derivative test to verify it's a local min. And if we did, we would see it is. It's a little tricky here to do that because you got to think about the sign, positive or negative, of this thing. If you're careful, you can verify it's negative when r is just less than this number, and positive when r is just bigger, making it a min. It's actually a little easier in this example, I think, to use the second derivative test. The second derivative, either written with Leibniz notation or with prime notation, differentiate this thing. Derivative of 4 pi r will be 4 pi. Differentiate this thing, the -2 comes down. -2 times -80 is positive 160, r to the -3. All I really care about is the fact that this is positive if r is positive. And know that negative exponent doesn't make the quantity negative. The negative exponent means another way to think of this function is 4 pi plus 160 over r to the positive 3 power. And yeah, this is definitely positive if r is positive. This would be enough to guarantee there's a local minimum here because the graph is concave up. Second derivative is positive. In fact, you could argue more. You could say since the second derivative is always positive when r is positive, the graph is always concave up when r is positive, it's got to be a global min. It can't come back down again. What does the graph of f look like? What does the graph of this function look like? You actually can draw it, well, of course, with your technology, but you can actually make sense out of the graph of this without calculus and without technology. When r is very large, 100, 1,000, 1,000,000, that quantity, 80 over r, is very small and contributes very little to the function output. The function acts like 2 pi r squared when r is large, which is quadratic. When r is small, close to 0, that's small. And this is large. The function acts like 80 over r when r is close to 0, which has a vertical asymptote at r equals 0, comes down like that. Add those two functions. Looks like this at the extreme. In between, it's going to have a min somewhere. And we know the min we found to be at cube root of 20 over pi, about 1.853. I could plug it into my calculator, pick a window, try to see that kind of graph. I have not figured out how high the window has to go to see this graph. I've not figured out the global minimum value, second coordinate. What is the minimum surface area? I haven't figured that out. Let's go ahead and approximate it now. I'll plug this number, this cube root, into this function. I'll use the previous answer key. I'm plugging in right there. Plus 80 over the previous answer. Whoops. I don't like when my calculator does that. Plus 80 over the previous answer. About 64.747. 64.747. What are the units for this? The units for R are in, again, inches. Of course, the units for volume are cubic inches, but this is a surface area. It's square inches. If you were asked for the minimum surface area, that's not what we were asked. We were asked for the dimensions of the can. But if you were asked for the minimum surface area, you would say the minimum surface area is this many square inches when the radius is this many inches. But the question said, what are the dimensions of the can? Meaning, what's the radius and the height? I haven't figured out the height yet. How to do that? Use the constraint. So once again, take our 1.85336.109 for R, now plug it into that equation to get the corresponding height. 40 divided by pi times the previous answer squared. Corresponding height's about 3.707 inches. I'm noticing something very interesting here. It looks like the height might be exactly twice the radius. Divide that height by 2. Oh, lo and behold, I get the radius. How about that? What this is telling you is that the actual amount of volume is irrelevant. It's hinting at least, the fact that as long as you got a cylinder of a fixed volume, the dimensions that are going to give the minimum surface area will always have a height that's double the radius, which means the height equals the diameter of the circle. Wow. That seems kind of profound. For a cylinder that includes the top and the bottom, and of course the side, when you minimize the surface area for a given volume, the diameter and the height will be equal to each other, is what this is hinting at. And that does turn out to be true. Now, if we took off the top, it does change the answer. If it's an open cylinder, no top, it changes this function. This 2 goes away, and it does change the answer. But if we do include the top, then that's interesting. The diameter equals the height. And maybe not unexpected. That took a while. Example 2 is very difficult. I think we better skip example 2. Let's end class today with example 3. I think it is still worthwhile for you to study example 2, but it's pretty challenging. In example 3, we see some curves. Y equals square root of x is the actual curve that you see there. X equals 9 is a curve that's really a vertical line. Y equals 0 is really the x-axis. And we see a rectangle with vertical sides at x equals a and x equals 9. The question says, find the dimensions of the rectangle having maximum possible area. Find the dimensions of the rectangle having maximum possible area. We got to figure out the base and the height. Okay, I've redrawn it now. Again, the problem says find the dimensions of the rectangle that has the maximum possible area. Huh. So what's the objective and what's the constraint? Let's write the objective first this time. The objective, the thing we want to do, that's why it's called an objective, is to maximize the area. Maximize A, the area of the rectangle. Base times height. What's the base? 9 minus A. I don't know what A is. That's part of what I got to figure out. What's the height? That seems less clear, doesn't it? Oh, it's easier to look over here than it is over here. What's that height? Think about what's relevant. What's the relevance of that graph? That height is square root of A, right? So the area of the rectangle is base 9 minus A times the height, square root of A. Effectively, the height being square root of A is the constraint. If I had a different function here, I'd get a different height. So effectively, that's the constraint, and I don't have to bother doing any solving. I just see that's what's constraining what can happen. So this is the function I got to maximize. For what values of A? Look at the picture. A has got to be somewhere between 0 and 9. Something interesting here. It cannot possibly be maximized at A equals 0 or A equals 9, can it? Because if A is 0, then, well, the rectangle doesn't have any height. It's a line with 0 area. And if A is 9, the rectangle is this line. If A is close to 0, the rectangle looks like this. If A is close to 9, the rectangle looks like this. Either extreme can't be the answer. The answer has got to be somewhere in the middle. We do have a closed and bounded interval here, so we will be guaranteed that a global max will exist by the extreme value theorem. For the purposes of differentiation, let's write the function like that, and let's give it a name like, oh, how about f of A? Capital A equals f of little a. Oh, this is fun. What's dA? You got to humor yourself somehow. What's dA? The derivative of capital A with respect to little a. It's f prime of A. It's 9 halves A to the negative 1/2 minus 3 halves A to the 1/2, right? I want to set this equal to 0 and solve for A. Is that really possible? Let's rewrite this as 9 over 2 square root of A minus 3 square root of A over 2 equals 0. And then add that to both sides. It looks like cross multiplication is going to be useful again. If I cross multiply here, 9 times 2 is 18. 3 times 2 is 6. Square root of A times itself is A. It looks like A is 3. If I've not made a mistake. Does that really work? Is 9 over 2 square root of 3 really equal to 3 square root of 3 over 2? They don't look the same, do they? But if I rationalize the denominator here, maybe we will see something that makes them look the same. Maybe. Yeah, we get some cancellation. They are the same. A equals 3 is our critical value. Is it really giving a global max? Well, we could use the technique we talked about on Wednesday. Make a table of values, We know at the endpoints, 0 and 9, the answer is 0. If you plug in 0, you definitely get 0. Minus 0 is 0. If you plug in 9 into f, square root of 9 is 3. 9 times 3 is 27. 9 to the 3 halves is also 27. Because 3 halves power means first take the square root, then cube it. What's the value at 3? It would be 9 times square root of 3. I'm plugging in a equals 3 minus 3 to the 3 halves, which would be 3 square root of 3. This can be simplified to 6 square root of 3. So the global max definitely occurs when a is 3. The maximum area is 6 times square root of 3. About 10.39. And if we were asked for the dimensions of the rectangle, which I think we were, well, a is 3, so 9 minus a is 6. The base is 6. And the height is square root of 3. Dimensions would be 6 by square root of 3. Square root of 3 is about 1.7. 6 by about 1.7. The 6 comes from 9 minus a. A was 3.